When your model runs slowly, is the real bottleneck compute, or is it memory, precision, or both? In this course, you'll see how H100 GPUs, Google TPUs, and Huawei Ascend NPUs balance flops, bandwidth, and numeric formats to unlock actual performance, not just theoretical peak. Most modern accelerators sit partially idle, not because they lack flops, but because they're waiting on data. In deep learning, memory bandwidth and capacity usually throttle you more than raw compute. You have two major levers. First, move data more efficiently by using the memory hierarchy well. Better locality, fewer transfers, smarter caching. Second, make the data smaller with lower precision, quantization, and sparsity. The goal of good systems engineering is simple. Keep those compute units continuously fed. Imagine the compute units as the center of a target. Closest in are registers and small on-chip memories, extremely fast but tiny. Around that is high-bandwidth memory like HBM, still quick, with more capacity. Further out sits host DRAM, and then SSD or NVMe, huge capacity, but much slower. Efficient accelerators, whether CUDA GPUs, TPUs, or Ascend NPUs, try to reuse data as much as possible in those inner rings before spilling to the outer, slower layers. On NVIDIA GPUs, you get a lot of manual control over data flow. Each streaming multiprocessor has fast registers and an L1 or shared memory region that you, or the framework, explicitly manage. Typically, tiles of data move from high-bandwidth HBM through the L2 cache into shared memory and finally into registers for computation. When tiling is done well, you maximize data reuse close to the compute units and hide much of the latency of going out to HBM. TPUs and Ascend NPUs push more responsibility onto the compiler to choreograph data movement. Instead of manually managing shared memory like on CUDA, XLA and the scan toolchain decide how tensors are tiled, buffered, and prefetched. Their job is to stream data through matrix engines in a very regular pattern and avoid random accesses. This is excellent for large static graphs, but less flexible when your model has lots of dynamic shapes or control flow. Floating point formats are just different ways to spend a limited number of bits. FP32 uses many bits for the mantissa, giving high precision and a huge dynamic range, but it's expensive to compute on. FP16 trades exponent bits for mantissa bits. You keep decent precision, but the smaller exponent range means tiny gradients can underflow to zero. BF16 flips that trade-off. It keeps FP32's exponent range and shrinks mantissa precision, which protects you from underflow while still being fast on modern accelerators. Precision is one of the biggest performance levers you control across these accelerators. NVIDIA offers the widest menu: FP32 for safety, plus TF32, FP16, BF16, and INT8, all with strong tensor core support. TPUs are optimized around BF16. That's XLA's default, and usually the sweet spot for training. Ascend also leans into low precision, with FP16, BF16, and INT8 heavily optimized in its matrix engines. If you align your training precision with each platform's native path, 2-4 by throughput gains are common. Mixed precision training runs most of the heavy math in low precision, like BF16 or FP16, while keeping a safe FP32 copy of the weights in the background. Gradients flow through the network in low precision, but before they get too small, we scale the loss up so those gradients don't underflow. The optimizer then updates the high-precision master weights. This loop cuts memory use and boosts throughput, yet keeps training numerically stable. When we talk about model memory, parameters are actually the predictable part. They're fixed once you choose model size and precision. Activations come next. They grow mainly with batch size and sequence length, and they're what hit you during training, not inference. The real hidden giant is optimizer state. Atom, for example, keeps several FP32 copies of each parameter, often using 2 to 3 times more memory than the weights themselves. Across all accelerators, understanding these three pieces explains most out-of-memory errors. Batch size is where hardware really shows its personality. As you grow the batch, memory fills in a step-like way until you suddenly hit out of memory. H100 and H200 give you the tallest wall per device thanks to huge HBM, so you can keep increasing local batch before you break. TPUs attack the problem differently, spreading a large global batch across many chips in a pod. Ascend leans on sizable clusters as well, scaling out data parallelism to mimic very large batches. Sequence length is one of the easiest ways to accidentally blow up accelerator memory. In naive self-attention, both compute and memory grow with L squared. So if you double the context window from 4K tokens to 8K, you don't just double memory, you roughly quadruple it. Even huge H100 TPU or Ascend devices can run out of memory very quickly when you push to very long sequences or combine them with big batches. Each vendor uses software tricks to work around these memory limits. On NVIDIA, flash attention restructures attention so most work happens in fast-on-chip SRAM, dramatically cutting expensive HBM traffic. On TPUs, XLA compiles attention into tiles that stay inside the systolic array, minimizing movement to external memory. On Huawei Ascend, CANN aggressively fuses operators so partial results never leave the chip between layers. Different mechanisms, same goal. Keep data local and squeeze more performance out of fixed hardware. When you configure each platform, the main knob you turn is different. On CUDA GPUs, performance often comes from careful memory behavior, making sure kernels and batches fit cleanly in HBM, and using tensor cores with TF32 or BF16. On TPUs, your leverage is XLA, shaping a mostly static graph using BF16 and scaling with large data parallel batches across chips. On Ascend, you focus on CANN operator fusion, FP16 or BF16 cube units, and per-core batch limits. To make this concrete, here's a simple checklist you can actually apply. First, keep data on chip as long as possible. Prefer SRAM and HBM, and minimize back and forth transfers with the host. Second, assume mixed precision by default. BF16 or FP16 for heavy tensor math. FP32 only where stability really matters. Third, tune batch size and sequence length together so you stay within memory. And finally, lean on the vendor toolchains, flash attention, XLA, and CANN, before attempting custom low-level tweaks.